The rise of AI has been largely driven by one tool in AI called machine learning. In this video, you learn what is machine learning so that by the end, you hopefully be able to start thinking how machine learning might be applied to your company or to your industry. The most commonly used type of machine learning is a type of AI that learns A to B or input to output mappings. And this is called supervised learning. Let's see some examples. If the input A is an email and the output B you want is this email spam or not, 0 or 1, then this is the core piece of AI used to build a spam filter. Or if the input A is an audio clip and the AI's job is to output the text transcript, then this is speech recognition. More examples, if you want to input English and have it output a different language, Chinese, Spanish, something else, then this is machine translation. Or the most lucrative form of supervised learning of this type of machine learning may be online advertising, where all the large online ad platforms have a piece of AI that inputs some information about an ad and some information about you and tries to figure out will you click on this ad or not. And by showing you the ads that you're most likely to click on, this turns out to be very lucrative. Maybe not the most inspiring application, but certainly having a huge economic impact today. Or if you want to build a self-driving car, one of the key pieces of AI is an AI that takes as input an image and some information from the radar or from other sensors and outputs the position of other cars, so your self-driving car can avoid the other cars. Or in manufacturing, I've actually done a lot of work in manufacturing where you would take as input a picture of something you've just manufactured, such as a picture of a cell phone coming off an assembly line. This is a picture of a phone, not a picture taken by a phone. And you want to output, is there a scratch or is there a dent or some other defect on this thing you've just manufactured? And this is visual inspection, which is helping manufacturers reduce or prevent defects in the things that they're making. This type of AI, called supervised learning, just learns input to output or A to B mappings. And on one hand, input to output, A to B, seems quite limiting, but when you find the right application scenario, this can be incredibly valuable. Now, the idea of supervised learning has been around for many decades, but it's really taken off in the last few years. Why is this? When my friends ask me, hey Andrew, why is supervised learning taking off now? There's a picture I draw for them, and I want to show you this picture now. And you may be able to draw this picture for others that ask you the same question as well. Let's say on the horizontal axis, you plot the amount of data you have for a task. So for speech recognition, this might be the amount of audio data and transcripts you have. In a lot of industries, the amount of data you have access to has really grown over the last couple of decades, thanks to the rise of the internet, the rise of computers. A lot of what used to be, say, pieces of paper are now instead recorded on a digital computer. So we've just been getting more and more data. Now, let's say on the vertical axis, you plot the performance of an AI system. It turns out that if you use a traditional AI system, then the performance would grow like this. That as you feed it more data, its performance gets a bit better, but beyond a certain point, it did not get that much better. So it's as if your speech recognition system did not get that much more accurate, or your online advertising system didn't get that much more accurate at showing the most relevant ads, even as you showed it more data. AI has really taken off recently due to the rise of neural networks and deep learning. I'll define these terms more precisely in a later video, so don't worry too much about what it means for now. But with modern AI, with neural networks and deep learning, what we saw was that if you train a small neural network, then the performance. You may have heard that data is really important for building AI systems, but what is data really? Let's take a look. Let's look at an example of a table of data, which we also call a data set. If you're trying to figure out how to price houses that you're trying to buy or sell, you might collect a data set like this, and this can be just a spreadsheet, like an Excel spreadsheet of data, where one column is the size of the house, say in square feet or square meters, and the second column is the price of the house. And so if you're trying to build an AI system or a machine learning system to help you set prices for houses or figure out if a house is priced appropriately, you might decide that the size of the house is A and the price of the house is B, and have an AI system learn this input to output or A to B mapping. Now, rather than just pricing a house based on the size, you might say, well, let's also collect data on the number of bedrooms of this house. In that case, A can be both of these first two columns, and B can be just the price of the house. So given a table of data, given a data set, it's actually up to you, up to your business use case to decide what is A and what is B. Data is often unique to your business, and this is an example of a data set that a real estate agency might have if they're trying to help price houses. And it's up to you to decide what is A and what is B, and how to choose these definitions of A and B to make it valuable for your business. As another example, if you have a certain budget and you want to decide what is the size of house you can afford, then you might decide that the input A is how much does someone spend, and B is just the size of the house. You might have heard terminology from AI such as machine learning or data science or neural networks or deep learning. What do these terms mean? In this video, you'll see what is this terminology of the most important concepts of AI so that you will speak with others about it and start thinking how these things could apply in your business. Let's get started. Let's say you have a housing data set like this with the size of the house, number of bedrooms, number of bathrooms, whether the house is newly renovated, as well as the price. If you want to build a mobile app to help people price houses, so this would be the input A, and this would be the output B, then this would be a machine learning system. In particular, it'd be one of those machine learning systems that learns input to output or A to B mappings. So machine learning often results in a running AI system. So it's a piece of software that any time of day, any time of night can automatically input A, these properties of a house, and outputs B. So if you have an AI system running, serving dozens or hundreds or thousands of millions of users, that's usually a machine learning system. In contrast, here's something else you might want to do, which is to have a team analyze your data set in order to gain insights. So a team might come up with a conclusion like, hey, did you know if you have two houses of a similar size, of a similar square footage, if the house has 3 bedrooms, then they cost a lot more than the house with 2 bedrooms, even if the square footage is the same. Or did you know that newly renovated homes have a 15% premium? And this could help you make decisions such as, given a similar square footage, do you want to build a 2-bedroom or a 3-bedroom size in order to maximize value? Or is it worth an investment to renovate a home in the hope that the renovation increases the price you can sell a house for? So these would be examples of data science projects, where the output of a data science project is a set of insights that can help you make business decisions, such as what type of house to build or whether to invest in renovation. The boundaries between these two terms, machine learning and data science, are actually a little bit fuzzy, and these terms are not used consistently even in industry today. But what I'm giving here is maybe the most commonly used definitions of these terms, but you will not find universal adherence to these definitions. To formalize these two notions a bit more, machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. This is a definition by Arthur Samuel many decades ago. Arthur Samuel was one of the pioneers of machine learning who was famous for building a checkers playing program that could play checkers even better than he himself, the inventor, could play the game. So a machine learning project will often result in a piece of software that runs, that outputs B given A. In contrast, data science is the science of extracting knowledge and insights from data. And so the output of a data science project is often a slide deck, a PowerPoint presentation that summarizes conclusions for executives to take business actions, or that summarizes conclusions for a product team to decide how to improve a website. Let me give an example of machine learning versus data science in the online advertising industry. Today, the large ad platforms all have a piece of AI that quickly tells them what's the ad you are most likely to click on. So that's a machine learning system, and this turns out to be incredibly lucrative. AI system that inputs information about you and about the ad and outputs will you click on this or not. These systems are running 24/7, and these are machine learning systems that drive ad revenue for these companies. So there's a piece of software that runs. In contrast, I've also done data science projects in the online advertising industry. If analyzing data tells you, for example, that the travel industry is not buying a lot of ads, but if you send more salespeople to sell ads to travel companies, you could convince them to use more advertising. Then that would be an example of a data science project and the data science conclusion that results in executives deciding to ask the sales team to spend more time reaching out to the travel industry. So even in one company, you may have different machine learning and data science projects, both of which can be incredibly valuable. You may have also heard of deep learning. So what is deep learning? Let's say you want to predict housing prices. You want to price houses. So you have an input that tells you the size of the house, number of bedrooms, number of bathrooms, and whether it's newly renovated. One of the most effective ways to price houses, given this input A, would be to feed it to this thing here in order to have it output the price. This big thing in the middle is called a neural network, and sometimes we also call it an artificial neural network. And that's to distinguish it from the neural network that is in your brain. So the human brain is made up of neurons, and so when we say artificial neural network, that's just to emphasize that this is not the biological brain, but instead it's a piece of software. And what a neural network does, or an artificial neural network does, is takes this input A, which is all of these four things, and then output B, which is the estimated price of a house. Now, in a later optional video this week, I'll show you more what this artificial neural network really is. But all of human cognition is made up of neurons in your brain passing electrical impulses, passing little messages to each other. And when we draw a picture of an artificial neural network, there's a very loose analogy to the brain. And these little circles are called artificial neurons, or just neurons for short, that also passes neurons to each other. And this big artificial neural network is just a big mathematical equation that tells it, given the inputs A, how do you compute the price B? In case it seems like there are a lot of details here, don't worry about it. We'll talk more about these details later. But the key takeaways are that a neural network is a very effective technique for learning A to B or input to output mappings. And today, the terms neural network and deep learning are used almost interchangeably. They mean essentially the same thing. Many decades ago, this type of software was called a neural network, but in recent years, we found that, deep learning was just a much better sounding brand. And so that, for better or worse, is the term that's been taking off recently. So what do neural networks or artificial neural networks have to do with the brain? It turns out almost nothing. Neural networks were originally inspired by the brain, but the details of how they work are almost completely unrelated to how biological brains work. So I was very cautious today about making any analogies between artificial neural networks and the biological brain, even though there was some loose inspiration there. So AI has many different tools. In this video, you learned about what are machine learning and data science, and also what is deep learning and what's a neural network. You might also hear in the media other buzzwords like unsupervised learning, reinforcement learning, graphical models, planning knowledge graph, and so on. And you don't need to know what all of these other terms mean, but these are just other tools for getting AI systems to make computers act intelligently. And I try to give you a sense of what some of these terms mean in later videos as well. But the most important tools that I hope you know about are machine learning and data science, as well as deep learning and neural networks, which are a very powerful way to do machine learning and sometimes data science. If we were to draw a Venn diagram showing how all these concepts fit together, this is what it might look like. AI is this huge set of tools for making computers behave intelligently. Of AI, the biggest subset is probably tools from machine learning, but AI does have other tools than machine learning, such as some of these buzzwords are listed at the bottom. And of machine learning, the part of machine learning that's most important these days is neural networks or deep learning. which is a very powerful set of tools for carrying out supervised learning or A to B mappings, as well as some other things. But there are also other machine learning tools that are not just deep learning tools. So how does data science fit into this picture? There is inconsistency in how the terminology is used. Some people will tell you data science is a subset of AI. Some people will tell you AI is a subset of data science. It depends a bit on who you ask. But I would say that data science is maybe a cross-cutting subset of all of these tools that uses many tools from AI, machine learning, and deep learning, but has some other separate tools as well that solves a very set of important problems in driving business insights. In this video, you saw what is machine learning, what is data science, and what is deep learning and neural networks. I hope this gives you a sense of the most common and important terminology used in AI, and you can start thinking about how these things might apply to your company. Now, what does it mean for a company to be good at AI? Let's talk about that in the next video. What makes a company good at AI? And perhaps even more importantly, what will it take for your company to become great at using AI? I had previously led the Google Brain team and Baidu's AI group, which had respectively helped Google and Baidu become great AI companies. So what can you do for your company? There's a lesson I had learned watching the rise of the internet that I think will be relevant to how all of us navigate the rise of AI. Let's take a look. A lesson we learned from the rise of the internet was that if you take your favorite shopping mall, so my wife and I sometimes shop at Stanford Shopping Center, and you build a website for the shopping mall, maybe sell things on the website, that by itself does not turn the shopping mall into an internet company. In fact, a few years ago, I was speaking with the CEO of a large retail company who said to me, "Hey, Andrew, I have a website. I sell things on the website. Amazon has a website. Amazon sells things on the website. It's the same thing." But of course it wasn't. And a shopping mall with a website isn't the same thing as a first-class internet company. So what is it that defines an internet company if it isn't just whether or not you sell things on the website? I think an internet company is a company that does the things the internet lets you do really well. For example, we engage in pervasive A/B testing, meaning we routinely throw up two different versions of a website and see which one works better because we can, and so we learn much faster. Whereas in a traditional shopping mall, it's very difficult to have two shopping malls in two parallel universes, and you can only maybe change things around every quarter or every 6 months. Internet companies tend to have very short iteration times. You can ship a new product every week or maybe even every day because you can. Whereas a shopping mall can be redesigned and re-architected only every several months. Internet companies also tend to push decision-making down from the CEO to the engineers and to other specialized roles, such as the product managers. This is in contrast to a traditional shopping mall where you can maybe have the CEO just decide all the key decisions and then just everyone does what the CEO says. And it turns out that traditional model doesn't work in the internet era because only the engineers and other specialized roles like product managers know enough about the technology and the product and the users to make great decisions. So these are some of the things that internet companies do in order to make sure they do the things that the internet lets them do really well. This is a lesson we learned from the internet era. How about the AI era? I think that today you can take any company and have it use a few neural networks or a few deep learning algorithms. That by itself does not turn the company into an AI company. Instead, what makes a great AI company, sometimes an AI first company, is, are you doing the things that AI lets you do really well? For example, AI companies are very good at strategic data acquisition. This is why many of the large consumer tech companies may have free products that do not monetize, and it allows them to acquire data that they can monetize elsewhere. So I've led strategy teams where we would deliberately launch products that do not make any money just for the sake of data acquisition. And thinking through how to get data is a key part of the great AI companies. AI companies tend to have unified data warehouses. If you have 50 different databases or 50 different data warehouses under the control of 50 different vice presidents, then it'll be impossible for an engineer to get the data into one place so that they can connect the dots and spot the patterns. So many great AI companies have preemptively invested in bringing the data together into a single data warehouse to increase the odds that the teams can connect the dots. Subject, of course, to privacy guarantees and also to data regulations such as GDPR in Europe. AI companies are very good at spotting automation opportunities. We're very good at seeing, oh, let's insert a supervised learning algorithm and have an A to B mapping here so that we don't have to have people do these tasks. Instead, we can automate it. AI companies also have many new roles, such as the MLE or machine learning engineer, and new ways of dividing up tasks among different members of a team. So for a company to become good at AI means architecting the company to do the things that AI makes it possible to do really well. Now, for a company to become good at AI does require a process. In fact, 10 years ago, Google and Baidu, as well as companies like Facebook and Microsoft that I was not a part of, were not great AI companies the way that they are today. So how can a company become good at AI? It turns out that becoming good at AI is not a mysterious, magical process. Instead, there is a systematic process through which many companies, almost any big company, can become good at AI. This is the 5-step AI transformation playbook that I recommend to companies that want to become effective at using AI. I'll give a brief overview of the playbook here and then go into detail in a later week. Step 1 is to execute pilot projects to gain momentum. So just do a few small projects to get a better sense of what AI can and cannot do and get a better sense of what doing an AI project feels like. And this you could do in-house or you can also do with an outsourced team. But eventually you then need to do step 2, which is to build an in-house AI team and provide broad AI training, not just to the engineers, but also to the managers, division leaders, and executives on how to think about AI. After doing this, or as you're doing this, you have a better sense of what AI is, and then it's important for many companies to develop an AI strategy. And finally, to align internal and external communications so that all your stakeholders, from employees, customers, and investors, are aligned with how your company is navigating the rise of AI. AI has created tremendous value in the software industry and will continue to do so. It will also create tremendous value outside the software industry. If you can help your company become good at AI, I hope you can play a leading role in creating a lot of this value. In this video, you saw what is it that makes a company a good AI company, and also briefly the AI transformation playbook, which I'll go into much greater detail on in a later week as a roadmap for helping companies become great at AI. If you're interested, there is also published online an AI transformation playbook that goes into these 5 steps in greater detail, but you'll see more of these in a later week as well. Now, one of the challenges of doing AI projects, such as the pilot projects in step 1, is in this video and the next video, I hope to help you develop intuition about what AI can and cannot do. In practice, before I commit to a specific AI project, I'll usually have either myself or engineers do technical diligence on the project to make sure that it is feasible. This means look at the data, look at the input and output A and B, and just thinking through if this is something AI can really do. What I've seen, unfortunately, is that some CEOs can have an overinflated expectation of AI and can ask engineers to do things that today's AI just cannot do. One of the challenges is that the media, as well as the academic literature, tends to only report on positive results or success stories using AI. And we see a string of success stories and no failure stories. People sometimes think AI can do everything. And unfortunately, that's just not true. So what I want to do in this and the next video is to show you a few examples of what today's AI technology can do, but also what it cannot do. And I hope that this will help you hone your intuition about what might be more or less promising projects to select for your company. Previously, you saw this list of AI applications, from spam filtering to speech recognition to machine translation and so on. One imperfect rule of thumb you can use to decide what supervised learning may or may not be able to do is that pretty much anything you could do with a second of thought, we can probably now or soon automate using supervised learning, using this input-output mapping. So for example, in order to determine the position of other cars, that's something that you can do with less than a second. In order to tell if a phone is scratched, you can look at it and you can kind of tell in less than a second. In order to understand, or at least transcribe what was said, it doesn't take that many seconds of thought. And while this is an imperfect rule of thumb, it maybe gives you a way to quickly think of some examples of tasks that AI systems can do. Whereas in contrast, something that AI today cannot do would be to analyze a market and write a 50-page report. A human cannot write a 50-page market analysis report in a second, and it's very difficult. At least I don't know. And I don't think any team in the world today knows how to get an AI system to do market research and write an extended market report either. I found that one of the best ways to hone intuition is to look at concrete examples. So let's take a look at a specific example relating to customer support automation. Let's say you run a website that sells things, so an e-commerce company, and you have a customer support division that gets an email like this. The toy arrived 2 days late, so I wasn't able to give it to my niece for her birthday. Can I return it? If what you want is an AI system that looks at this and decides this is a refund request, so let me route it to my refund department, then I would say you have a good chance of building an AI system to do that. The AI system would take as input the customer text, what the customer emailed you, and it would output, is this a refund request, or is this a shipping problem, or is it a other request, in order to route this email to the most appropriate part of your customer support center. So the input A is the text, and the output B is one of these three outcomes. Is it a refund, or a shipping problem, or a shipping query, or is it a different request? So this is something that AI today can do. Here's something that AI today cannot do, which is if you want the AI to input an email and automatically generate a response like, oh, sorry to hear that. I hope your niece had a good birthday. Yes, we can help with, and so on. So for an AI to output a complicated piece of text like this today is very difficult by today's standards of AI. And in fact, to even empathize about the birthday of your niece, that is very difficult to do for every single possible type of email you might receive. Now, what would happen if you were to use a machine learning tool, like a deep learning algorithm, to try to do this anyway? So let's say you try to get an AI system to input the user's email and output a 2 to 3 paragraph empathetic and appropriate response. And let's say that you have a model-sized data set, like 1,000 examples of user emails and appropriate responses. It turns out if you run an AI system on this type of data, on a small data set, like 1,000 examples, this may be the performance you get, which is if a user emails, my box is damaged, it'll say, thank you for your email. If it says, where did I write a review? Thank you for your email. What's the return policy? Thank you for your email. But the problem with building this type of AI is that with just 1,000 examples, there's just not enough data for an AI system to learn how to write 2 to 3 paragraph appropriate and empathetic responses. So it may end up just generating the same very simple response like thank you for your email, no matter what the customer is sending you. Another thing that could go wrong, another way for an AI system to fail is if it generates gibberish, such as, when are my box arriving? And it says, thank, yes, now, your kind of gibberish. And this is a hard enough problem that even with 10,000 or 100,000 email examples, I don't know if that would be enough data for an AI system to do this well. The rules for what AI can and cannot do are not hard and fast, and I usually end up having to ask engineering teams to sometimes spend a few weeks doing deep technical diligence to decide for myself if a project is feasible. But to hone your intuitions, to help you quickly filter feasible and not feasible projects, here are a couple other rules of thumb about what makes a machine learning problem easier or more likely to be feasible. One, learning a simple concept is more likely to be feasible. Well, what does a simple concept mean? There's no formal definition of that, but if it's something that takes you less than a second of mental thought, or a very, very small number of seconds of mental thought to come up with a conclusion, then that would lean toward it being a simple concept. So you're looking outside the window of a self-driving car to spot the other cars. That would be a relatively simple concept. Whereas how to write an empathetic response to a complicated user complaint, that would be less of a simple concept. Second, a machine learning problem is more likely to be feasible if you have lots of data available. And here, data means both the input A and the output B that you want the AI system to have in your A to B input-output mapping. So, for example, in the customer support application, the input A would be examples of emails from customers, and B could be labeling each of these customer emails as to whether it is a refund request or a shipping query or some other problem, one of three outcomes. And if you have thousands of emails with both A and B, then the odds of you being able to build a machine learning system to do that would be pretty good. AI is the new electricity and is transforming every industry, but it's also not magic and it can't do everything under the sun. I hope that this video started to help you hone your intuitions about what it can and cannot do and increase the odds of your selecting feasible and valuable projects for maybe your teams to try working on. In order to help you continue developing your intuition, I would like to show you more examples of what AI can and cannot do. Let's go on to the next video. One of the challenges of becoming good at recognizing what AI can and cannot do is that it does take seeing a few examples of concrete successes and failures of AI. And if you work on an average of, say, one new AI project a year, then to see 3 examples would take you 3 years of work experience, and that's just a long time. What I hope to do, both in the previous video and in this video, is to quickly show you a few examples of AI successes and failures, or what it can and cannot do, so that in a much shorter time, you can see multiple concrete examples to help hone your intuition and select valuable projects. So let's take a look at a few more examples. Let's say you're building a self-driving car. Here's something that AI can do pretty well, which is to take a picture of what's in front of your car, and maybe just using a camera, maybe using other sensors as well, such as radar or LiDAR. And then to figure out what is the position or where are the other cars. So this would be an AI where the input A is a picture of what's in front of your car, or maybe both a picture as well as radar and other sensor readings. And the output B is where are the other cars. And today, the self-driving car industry has figured out how to collect enough data and has pretty good algorithms for doing this reasonably well. So that's what AI today can do. Here's an example of something that today's AI cannot do, or at least would be very difficult using today's AI, which is to input a picture and output the intention or whatever the human is trying to gesture at your car. So here's a construction worker holding out a hand to ask your car to stop. Here's a hitchhiker trying to wave a car over. Here's a bicyclist raising the left hand to indicate that they want to turn left. And so if you were to try to build a system to learn an A to B mapping, where the input A is a short video of a human gesturing at your car, and the output B is what's the intention or what does this person want, that today is very difficult to do. Part of the problem is that the number of ways people gesture at you is very, very large. Imagine all the hand gestures someone could conceivably use to ask you to slow down or go or stop. the number of ways that people could gesture at you is just very, very large. And so it's difficult to collect enough data from enough thousands or tens of thousands of different people gesturing at you in all of these different ways to capture the richness of human gestures. So learning from a video to what this person wants is actually a somewhat complicated concept. In fact, even people have a hard time figuring out sometimes what someone waving at your car wants. And then second, because this is a safety critical application, you would want an AI that is extremely accurate in terms of figuring out, does the construction worker want you to stop or does he or she want you to go? And that makes it harder for an AI system as well. And so today, if you collect just say 10,000 pictures of other cars, many teams will be able to build an AI system that at least has a basic capability at detecting other cars. In contrast, even if you collect pictures or videos of 10,000 people, it's quite hard to track down 10,000 people waving at your car. Even with that data set, I think it's quite hard today to build an AI system to recognize human intention from the gestures at the very high level of accuracy needed in order to drive safely around these people. So that's why today, many self-driving car teams have some component for detecting other cars, and they do rely on that technology to drive safely. But very few self-driving car teams are trying to count on an AI system to recognize a huge diversity of human gestures and counting just on that to drive safely around people. Let's look at one more example. Say you want to build an AI system to look at X-ray images and diagnose pneumonia. So all of these are chest X-rays. So the input A could be the X-ray image and the output B can be the diagnosis. Does this patient have pneumonia or not? So that's something that AI can do. Something that AI cannot do would be to diagnose pneumonia from 10 images of a medical textbook chapter explaining pneumonia. A human can look at a small set of images, maybe just a few dozen images, and read a few paragraphs from a medical textbook and start to get a sense. But I actually don't know, given a medical textbook, what is A and what is B, or how to really pose this as an AI problem that know how to write a piece of software to solve if all you have is just 10 images and a few paragraphs of text that explain what pneumonia in a chest X-ray looks like. Whereas a young medical doctor might learn quite well reading a medical textbook and just looking at, maybe dozens of images. In contrast, an AI system isn't really able to do that today. To summarize, here are some of the strengths and weaknesses of machine learning. Machine learning tends to work well when you're trying to learn a simple concept, such as something that you could do with less than a second of mental thought, and when there's lots of data available. Machine learning tends to work poorly when you're trying to learn a complex concept from small amounts of data. A second underappreciated weakness of AI is that it tends to do poorly when it's asked to perform on new types of data that's different than the data it has seen in your data set. Let me explain with an example. Say you built a supervised learning system that uses A to B to learn to diagnose pneumonia from images like these. These are pretty high quality chest X-ray images. But now let's say you take this AI system and apply it at a different hospital or a different medical center where maybe the X-ray technician somehow strangely had the patients always lie at an angle, or sometimes there are these defects. I'm not sure if you can see the little scratches in the image, these little other objects lying on top of the patients. If the AI system has learned from data like that on your left, maybe taken from a high quality medical center, and you take this AI system and apply it to a different medical center that generates images like those on the right, then its performance will be quite poor as well. A good AI team will be able to ameliorate or to reduce some of these problems, but doing this is not that easy. And this is one of the things that AI is actually much weaker than humans. If a human has learned from images on the left, they're much more likely to be able to adapt to images like those on the right as they figure out that the patient's just lying at an angle. But an AI system can be much less robust than human doctors in generalizing or figuring out what to do with new types of data like this. I hope these examples are helping you hone your intuitions about what AI can and cannot do. In case the boundary between what it can and cannot do still seems fuzzy to you, don't worry, that's completely normal, completely okay. In fact, even today, I still can't look at a project and immediately tell if something is feasible or not. And I often still need small numbers of weeks of technical diligence before forming strong conviction about whether something is feasible or not. But I hope that these examples can at least help you start imagining some things in your company that might be feasible and might be worth exploring more. The next two videos after this are optional and are a non-technical description of what are neural networks and what is deep learning. Please feel free to watch those. And then next week, we'll go much more deeply into the process of what building an AI project would look like. Look forward to seeing you next week. The terms deep learning and neural network are used almost interchangeably in AI. And even though they're great for machine learning, there's also been a bit of hype and a bit of mystique about them. This video will demystify deep learning so that you have a sense of what deep learning and neural networks really are. Let's use an example from demand prediction. Let's say you run a website that sells t-shirts and you want to know, based on how you price the t-shirts, how many units you expect to sell, how many t-shirts you expect to sell. You might then create a data set like this, where the higher the price of the t-shirt, the lower the demand. So you might fit a straight line to this data, showing that as the price goes up, the demand goes down. Now, demand can never go below zero, so maybe you say that the demand will flatten out at zero, and beyond a certain point, you expect, pretty much no one to buy any t-shirts. It turns out this blue line is maybe the simplest possible neural network. You have as input the price, A, and you want it to output the estimated demand, B. So the way you would draw this as a neural network is that the price would be input to this little round thing there, and this little round thing outputs the estimated demand. In the terminology of AI, this little round thing here is called a neuron, or sometimes it's called an artificial neuron, and all it does is compute this blue curve that I've drawn here on the left. This is maybe the simplest possible neural network with a single artificial neuron that just inputs the price and outputs the estimated demand. If you think of this orange circle, this artificial neuron, as a little Lego brick, all that a neural network is if you take a lot of these Lego bricks and stack them on top of each other until you get a big pile or a big network of these neurons. Let's look at a more complex example. Suppose that instead of knowing only the price of the t-shirts, you also have the shipping costs that the customers will have to pay to get the t-shirts. Maybe you spend more or less on marketing in a given week. And you can also make the t-shirt out of a thick, heavy, expensive cotton or a much cheaper, more lightweight material. These are some of the factors that you think will affect the demand for your t-shirts. Let's see what a more complex neural network might look like. You know that your customers care a lot about affordability. So let's say you have one neuron, and let me draw this one in blue, whose job it is to estimate the affordability of the t-shirts. And because affordability is mainly a function of the price of the shirt and of the shipping costs. A second thing that will affect the demand for your t-shirts is awareness. How much are consumers aware that you're selling this t-shirt? So the main thing that affects awareness is going to be your marketing. So let me draw here a second artificial neuron that inputs your marketing budget, how much you spent on marketing, and outputs how aware are consumers of your t-shirt. Finally, the perceived quality of your product will also affect demand, and perceived quality would be affected by marketing. If the marketing tries to convince people this is a high quality t-shirt, and sometimes the price of something also affects perceived quality. So I'm going to draw here a third artificial neuron that inputs price marketing and material and tries to estimate the perceived quality of your t-shirts. Finally, now that the earlier neurons, these three blue neurons, have figured out how affordable, how much consumer awareness, and what's the perceived quality, you can then have one more neuron over here that takes as input these three factors and outputs the estimated demand. So this is a neural network, and its job is to learn to map from these four inputs, that's the input A, to the output B, the demand. So it learns this input to output, or A to B mapping. This is a fairly small neural network with just 4 artificial neurons. In practice, neural networks used today are much larger, with easily thousands, tens of thousands, or even much larger than that numbers of neurons. Now, there's just one final detail of this description that I want to clean up, which is that in the way I've described a neural network, it was as if you had to figure out that the key factors are affordability, awareness, and perceived quality. One of the wonderful things about using neural networks is that to train a neural network, in other words, to build a machine learning system using a neural network, all you have to do is give it the input A and the output B, and it figures out all of the things in the middle by itself. So to build a neural network, what you would do is feed it lots of data with the input A, and have a neural network that just looks like this, with a few blue neurons feeding to a yellow output neuron. And then you have to give it data with the demand B as well. And it's the software's job to figure out what these blue neurons should be computing so that it can completely automatically learn the most accurate possible function mapping from the input A to the output B. And it turns out that if you give this enough data and train a neural network that is big enough, this can do an incredibly good job mapping from inputs A to outputs B. So that's a neural network. It's a group of artificial neurons, each of which computes a relatively simple function, but when you stack enough of them together like Lego bricks, they can compute incredibly complicated functions that give you very accurate mappings from the input A to the output B. Now, in this video, you saw an example of neural networks applied to demand prediction. Let's go on to the next video to see a more complex example of neural networks applied to face recognition. In the last video, you saw how a neural network can be applied to demand prediction. But how can a neural network look at a picture and figure out what's in the picture, or listen to an audio clip and understand what is said in an audio clip? Let's take a look at a more complex example of applying a neural network to face recognition. Say you want to build a system to recognize people from pictures. How can a piece of software look at this picture and figure out the identity of the person in it? Let's zoom in to a little square like that to better understand how a computer sees pictures. Where you and I see a human eye, a computer instead sees that. It sees this grid of pixel brightness values that tells it for each of the pixels in the image, how bright is that pixel. If it were a black and white or a grayscale image, then each pixel would correspond to a single number telling you how bright is that pixel. If it's a color image, then each pixel would actually have 3 numbers corresponding to how bright are the red, green, and blue elements of that pixel. So the neural network's job is to take as input a lot of numbers like these and tell you the name of the person in the picture. In the last video, you saw how a neural network can take as input 4 numbers corresponding to the price, shipping cost, amount of marketing, and the cloth material of a t-shirt and output demand. In this example, the neural network just has to input a lot more numbers corresponding to all of the pixel brightness values of this picture. If the resolution of this picture is 1000 pixels by 1000 pixels, then that's 1,000,000 pixels. So if it were a black and white or a grayscale image, this neural network would take as input 1,000,000 numbers corresponding to the brightness of all 1 million pixels in this image. Or if it was a color image, it would take as input 3 million numbers corresponding to the red, green, and blue values of each of these 1 million pixels in this image. Similar to before, you will have many of these artificial neurons computing various values. And it's not your job to figure out what these neurons should compute. The neural network will figure it out by itself. But typically, when you give it an image, the neurons in the earlier parts of the neural network will learn to detect edges in pictures, and then a little bit later, it'll learn to detect parts of objects. So it may learn to detect eyes and noses and the shape of cheeks and the shape of mouths. And then the later neurons, further to the right, will learn to detect different shapes of faces. And it will finally put all this together to output the identity of the person in the image. And again, part of the magic of neural networks is that you don't really need to worry about what it is doing in the middle. All you need to do is give it a lot of data of pictures like this, A, as well as of the correct identity, B, and the learning algorithm will figure out by itself what each of these neurons in the middle should be computing. Congratulations on finishing all the videos for this week. You now know how machine learning and data science work. I look forward to seeing you in next week's videos as well, where you learn how to build your own machine learning or data science project. See you next week. Machine learning algorithms can learn input to output or A to B mappings. So how do you build a machine learning project? In this video, you learn what is the workflow of machine learning projects. Let's take a look. As a running example, I'm going to use speech recognition. So some of you may have an Amazon Echo or a Google Home or Apple Siri device or a Baidu DuerOS device in your homes. Some years back, I'd done some work on Google's speech recognition system, and it also led Baidu's DuerOS project. And today, I actually have a Amazon Echo in my kitchen. So every time I'm boiling an egg, I will say, Alexa, set timer for 3 minutes, and then it lets me know when the 3 minutes are up and my eggs are ready. So how do you build a speech recognition system that can recognize when you say Alexa, or Hey Google, or Hey Siri, or Hello Baidu? Let's go through the key steps of a machine learning project. And just for simplicity, I'm going to use Amazon Echo or detecting the Alexa keyword as this running example. If you want to build an AI system or build a machine learning system to figure out when a user has said the word Alexa, the first step is to collect data. So that means you would go around and get some people to say the word Alexa for you, and you record the audio of that. And you'd also get a bunch of people to say other words like hello, or say lots of other words and record the audio of that as well. Having collected a lot of audio data, a lot of these audio clips of people saying either Alexa or saying other things, step 2 is to then train the model. And this means you would use a machine learning algorithm to learn an input to output or A to B mapping, where the input A would be an audio clip, and in the case of the first audio clip above, hopefully it will tell you that the user said Alexa, and in the case of audio clip 2 shown on the right, hopefully the system will learn to recognize that the user has said hello. Whenever an AI team starts to train the model, meaning to learn the A to B or input-output mapping, what happens pretty much every time is the first attempt doesn't work well. And so invariably, the team will need to try many times. Or in AI, we call this iterate many times. You have to iterate many times until hopefully the model looks like it's good enough. The third step is to then actually deploy the model. And what that means is you put this AI software into an actual smart speaker and ship it to either a small group of test users or to a large group of users. What happens in a lot of AI products is that when you ship it, you see that it starts getting new data and it may not work as well as you had initially hoped. So, for example, I am from the UK, so I'm going to pick on the British, but let's say you had trained your speech recognition system on American accented speakers, and you then ship this smart speaker to the UK, and you start having British accented people say Alexa, then you may find that it doesn't recognize their speech as well as you had hoped. And when that happens, hopefully you can get data back of cases such as maybe British accented speakers was not working as well as you're hoping, and then use this data to maintain and to update the model. So to summarize, the key steps of a machine learning project are to collect data, to train the model, the A to B mapping, and then to deploy the model. And throughout these steps, there is often a lot of iteration, meaning fine-tuning or adapting the model to work better, or getting data back even after you've shipped it to hopefully make the product better, which may or may not be possible depending on whether you're able to get data back. Let's look at these 3 steps and see how they apply on the different projects on building a key component of a self-driving car. So remember the key steps of collect data, train model, and deploy model, since we'll revisit these 3 steps on the next slide. Let's say you're building a self-driving car. One of the key components of a self-driving car is a machine learning algorithm that takes as input, say, a picture of what's in front of your car and tells you where are the other cars. So what's the first step of building this machine learning system? Hopefully you remember from the last slide that the first step was to collect data. So if your goal is to have a machine learning algorithm that can take as input an image and output the position of other cars, the data you would need to collect would be both images as well as position of other cars that you want the AI system to output. So let's say you start off with a few pictures like this. These are the inputs A to the machine learning algorithm. You need to also tell it what is the output B you would want. And so for each of these pictures, you would draw a rectangle around the cars in the picture that you wanted to detect. And on this slide, I'm hand drawing these rectangles, but in practice, you would use some software that lets you draw perfect rectangles rather than these hand-drawn ones. And then having created this data set, what was the second step? Hope you remember that the second step was to train the model. Now, invariably, when your AI engineers start training a model, they'll find initially that it doesn't work that well. For example, given this picture, maybe the software, the first few tries, thinks that that is a car. And it's only by iterating many times that you hopefully get a better result, like figuring out that that is where the car actually is. Finally, what was the third step? It was to deploy the model. Of course, in the self-driving world, it's important to treat safety as number one and deploy model or to test the model only in ways that can preserve safety. But when you put this software in cars on the road, you may find that there are new types of vehicles, say golf cars, that the software isn't detecting very well. And so you would get data back, say pictures of these golf cars, use the new data to maintain and update the model so that hopefully you can have your AI software continually get better and better to the point where you end up with a software that can do a pretty good job detecting other cars from pictures like these. In this video, you learn what are the key steps of a machine learning project, which are to collect data, to train the model, and then to deploy the model. Next, let's take a look at what are the key steps or what is the workflow of a data science project. Let's go on to the next video. Unlike a machine learning project, the output of a data science project is often a set of actionable insights, a set of insights that may cause you to do things differently. So data science projects have a different workflow than machine learning projects. Let's take a look at what are the steps of a data science project. As our running example, let's say you want to optimize a sales funnel. Say you run an e-commerce or online shopping website that sells coffee mugs. And so for a user to buy a coffee mug from you, the sequence of steps they'll usually follow. First, they'll visit your website and take a look at the different coffee mugs on offer. Then eventually they have to get to a product page, and then they'll have to put it into their shopping cart and go to the shopping cart page. And then they'll finally have to check out. So if you want to optimize the sales funnel to make sure that as many people as possible get through all of these steps, how can you use data science to help with this problem? Let's look at the key steps of a data science project. The first step is to collect data. So on a website like the one we saw, you may have a data set that stores when different users go to different web pages. In this simple example, I'm assuming that you can figure out the country that the users are coming from, for example, by looking at their computer's address, called an IP address, and figuring out what is the country from which they're originating. But in practice, you could usually get quite a bit more data about users than just what country they're from. The second step is to then analyze the data. Your data science team may have a lot of ideas about what is affecting the performance of your sales funnel. For example, they may think that overseas customers are scared off by the international shipping costs, which is why a lot of people go to the checkout page but don't actually check out. And if that's true, then you might think about whether to put part of shipping costs into the actual product costs. Or your data science team may think there are blips in the data whenever there's a holiday. Maybe more people will shop around the holidays because they're buying gifts, or maybe fewer people will shop around the holidays because they're staying home rather than, sometimes shopping from their work computers. And in some countries, there may be time of day blips where in countries that observe a siesta, so a time of rest, like an afternoon rest, there may be fewer shoppers online, and so your sales may go down. And they might then suggest that you should spend fewer advertising dollars during the period of siesta because fewer people will go online to buy at that time. So a good data science team may have many ideas, and so they try many ideas, or we'll say iterate many times to get good insights. Finally, the data science team will distill these insights down to a smaller number of hypotheses about ideas of what could be going well and what could be going poorly, as well as a smaller number of suggested actions, such as incorporating shipping costs into the product cost rather than having it as a separate line item. When you take some of these suggested actions and deploy these changes to your website, you then start to get new data back as users behave differently now that you advertise differently at the time of siesta or have a different checkout policy. And then your data science team can continue to collect data and reanalyze the new data periodically to see if they can come up with even better hypotheses or even better actions over time. So the key steps of a data science project are to collect the data, to analyze the data, and then to suggest hypotheses and actions, and then to continue to get the data back and reanalyze the data periodically. Let's take this framework and apply it to a new problem, to optimizing a manufacturing line. And so we'll take these 3 steps and use them on the next slide as well. Let's say you run a factory that's manufacturing thousands of coffee mugs a month for sale, and you want to optimize the manufacturing line. So these are the key steps in manufacturing coffee mugs. Step 1 is to mix the clay, so make sure the appropriate amount of water is added. Step 2 is to take this clay and to shape the mugs. Then you have to add the glaze, so add the coloring, the protective cover. Then you have to heat this mug, and we call that firing the kiln. And finally, you would inspect the mug to make sure there aren't dents in the mug and it isn't cracked before you ship it to customers. So a common problem in manufacturing is to optimize the yield of this manufacturing line to make sure that as few damaged coffee mugs get produced as possible, because those are coffee mugs you have to throw away, resulting in time and material waste. What's the first step of a data science project? I hope you remember from the last slide that the first step is to collect data. So for example, you may save data about the different batches of clay that you've mix, such as who supplied the clay and how long did you mix it, or maybe how much moisture was in the clay, how much water did you add. You might also collect data about the different batches of mugs you made, so how much humidity was in that batch, what was the temperature in the kiln, and how long did you fire it in the kiln. Given all this data, you would then ask the data science team to analyze the data, and they would, as before, iterate many times to get good insights. And so they might find out, for example, that whenever the humidity is too low and the kiln temperature is too hot, that it cracks in the mug. Or they may find out that because it's warmer in the afternoon, that you need to adjust the humidity and the temperature depending on the time of day. Based on the insights from your data science team, you get suggestions for hypotheses and actions on how to change the operations of your manufacturing line in order to improve the productivity of the line. And when you deploy the changes, you then get new data back that you can reanalyze periodically so that you can keep on optimizing the performance of your manufacturing line. To summarize, the key steps of a data science project are to collect the data, to analyze the data, and then to suggest hypotheses and actions. In this video and the last video, you saw some examples of machine learning projects and data science projects. It turns out that machine learning and data science are affecting almost every single job function. What I want to do in the next video is show you how these ideas are affecting many job functions, including perhaps yours and certainly that of many of your colleagues. Let's go on to the next video. Data is transforming many different job functions. Whether you work in recruiting or sales or marketing or manufacturing or agriculture, data is probably transforming your job function. What's happened in the last few decades is the digitalization of our society. So rather than handing out paper surveys like these, surveys are more likely to be done in digital format. Or doctors still write some handwritten notes, but a doctor's handwritten note is increasingly likely to be a digital record. And so too it is in just about every single job function. And this availability of data means that there's a good chance that your job function can be helped with tools like data science or machine learning. Let's take a look. And in this video, I want to run through many different job functions and discuss how data science and machine learning can or will impact these different types of jobs. Let's start with sales. You've already seen in the last video how data science can be used to optimize a sales funnel. How about machine learning? If you're a salesperson, you may have a set of leads about different people that you could reach out to convince them to buy something from your company. Machine learning can help you prioritize these leads. So you might want to prioritize calling up the CEO of the large company rather than the intern at a much smaller company. And this type of automated lead sorting is making salespeople more efficient. Let's look at more examples. Let's say you're a manufacturing line manager. You've already seen how data science can help you optimize a manufacturing line. How about machine learning? One of the steps of this manufacturing process is the final inspection. And in fact, today in many factories, there can be hundreds or thousands of people using the human eye to check over objects, maybe coffee mugs, maybe other things, to see if there's scratches or dents, and that's called inspection. So machine learning can take as input a data set like this and learn to automatically figure out if a coffee mug is defective or not. And by automatically finding scratches or dents, it can reduce labor costs and also improve quality in your factory. This type of automated visual inspection is one of the technologies that I think will have a big impact on manufacturing. This is something I've been working on myself as well. Let's see more examples. How about recruiting? When recruiting someone to join your company, there may be a pretty predictable sequence of steps where your recruiter or someone else would send an email to a candidate, and then you'd have a phone call with them, bring them on site for an interview, and then extend an offer and maybe close the offer. Similar to how data science can be used to optimize a sales funnel, recruiting can also use data science to optimize a recruiting funnel. And in fact, many recruiting organizations are doing so today. For example, if you find that hardly anyone is making it from the phone screen step to the on-site interview step, then you may conclude that maybe too many people are getting to the phone screen stage, or maybe the people doing the phone screen are just being too tough and they should let more people get to the on-site interview stage. This type of data science is already having an impact on recruiting. What about machine learning projects? Well, one of the steps of recruiting is to screen a lot of resumes to decide who to reach out to. So you may have to look at one resume and says, yes, let's email them, look at a different one to say, no, let's not move ahead with this candidate. And machine learning is starting to make its way into automated resume screening. This does raise important ethical questions, such as making sure that your AI software does not exhibit undesirable forms of bias and treats people fairly, but machine learning is starting to make inroads into this, and I hope can do so while making sure that the systems are ethical and fair. In the final week of this AI for Everyone course, you also learn more about the issues of fairness and ethics in AI. What if you work in marketing? One of the common ways to optimize the performance of a website is called A/B testing, in which you launch two versions of a website. Here, version A has a red button, version B has a green button, and you measure which website causes people to click through more. So with this type of data, a data science team can help you gain insights and suggest hypotheses or actions for optimizing a website. How about machine learning and marketing? Today, a lot of websites will give customized product recommendations to show you the things you're most likely to want to buy, and this actually significantly increases sales on these websites. For example, a clothing website, after seeing the way I shop after a while, will hopefully just recommend blue shirts to me because that's frankly pretty much the only type of shirt I ever buy. But maybe other customers will have more diverse and more interesting recommendations than mine. But today, these customized product recommendations actually drive a large percentage of sales on many large online e-commerce websites. One last example from a totally different sector. Let's say you work in agriculture. Maybe you're a farmer working on a large industrial farm. How can data science help you? Today, farmers are already using data science for crop analytics, where you can take data on the soil conditions, the weather conditions, the prices of different crops in the market, and have data science teams make recommendations to what to plant, when to plant, so as to improve yields while maintaining the condition of the soil on your farm. This type of data science is and will play a bigger and bigger role in agriculture. Let's also look at a machine learning example. I think one of the most exciting changes to agriculture is precision agriculture. Here's a picture that I took on a farm with my cell phone. On the upper right is a cotton plant, and shown in the middle is a weed. And so with machine learning, we're starting to see products that can go onto the farms, take a picture like this, and spray a weed killer in a very precise way just onto the weed so that it gets rid of the weed, but without having to spray an excessive amount of weed killers. This type of machine learning technology is both helping farmers increase crop yields while also helping to preserve the environment. In this video, you saw how all of these job functions, everything from sales to recruiting to marketing to manufacturing to farming and agriculture, how all of these job functions are being affected by data science and by machine learning. It seems like there's a lot of different things you could do with AI, but how do you actually select a promising project to work on? Let's talk about that in the next video. If you want to try your hand at an AI project, how do you select a worthwhile project to work on? Don't expect an idea to necessarily come overnight. Sometimes it happens, but sometimes it also takes a few days or maybe a few weeks to come up with a worthy idea to pursue. In this video, you see a framework for brainstorming potentially exciting AI projects to pursue. Let's say you want to build an AI project for your business. You've already seen that AI can't do everything. And so there's going to be a certain set of things that is what AI can do. So let's let this circle represent the set of things that AI can do. Now, there's also going to be a certain set of things that is valuable for your business. So let's let this second circle represent a set of things that are valuable for your business. What you would like to do is try to select projects that are at the intersection of these two sets. So you select projects, hopefully, that are both feasible, that can be done with AI, and that are also valuable for your business. So AI experts will tend to have a good sense of what is and what isn't in the sets on the left, and domain experts, experts in your business, be it sales or marketing or agriculture or something else, will have a best sense of what is actually valuable for your business. So when brainstorming projects that AI can do and are valuable for your business, I will often bring together a team comprising both people knowledgeable about AI as well as experts in your business area to brainstorm together so that together they can try to identify projects at the intersection of both of these two sets. So sometimes we also call these cross-functional teams, and that just means a team that includes both AI experts as well as domain experts, meaning experts in your area of business. When brainstorming projects, there's a framework that I've used with a lot of companies that I've found to be useful. So let me share with you 3 principles or 3 ideas for how you can have a team brainstorm projects. First, even though there's been a lot of press coverage about AI automating jobs away, and this is an important societal issue that needs to be addressed, when thinking about concrete AI projects, I find it much more useful to think about automating tasks rather than automating jobs. Take call center operations. There are a lot of tasks that happen in the call center, ranging from people picking up the phone to answering phone calls, to replying to emails, to taking specific actions, such as issuing a refund on behalf of a customer request. But of all of these tasks that employees in the call center do, there may be one, call routing or email routing, that may be particularly amenable to machine learning automation. And it's by looking at all these tasks that the group of employees do and selecting one that may allow you to select the most fruitful project for automation in the near term. Let's look at another example, the job of a radiologist. There's been a lot of press about how AI may automate radiologists' jobs, but radiologists actually do a lot of things. They read x-rays, that's really important, but they also engage in their own continuing education. They consult with other doctors, they may mentor younger doctors, some of them also consult directly with patients. And so it's by looking at all of these tasks that a radiologist does that you may identify one of them, let's say AI assistance or AI automation for reading x-rays, that allows you to select the most fruitful projects to work on. So what I would recommend is, if you look at your business, think about the tasks that people do to see if you can identify just one of them or just a couple of them that may be automatable using machine learning. When I'm meeting CEOs of large companies to brainstorm AI projects for the company, a common question I'll also ask is, what are the main drivers of business value? And sometimes finding AI solutions or data science solutions to augment this can be very valuable. Finally, a third question that I've asked that's sometimes led to valuable project ideas is, what are the main pain points in your business? Some of them could be solved with AI, some of them can't be solved with AI, but by understanding the main pain points in the business, that can create a useful starting point for brainstorming AI projects as well. I have one last piece of advice for brainstorming AI projects, which is that you can make progress even without big data, even without tons of data. Now, don't get me wrong, having more data almost never hurts, other than maybe needing to pay a bit more for disk space or network bandwidth to transmit and store the data. Having more data almost always is only helpful, and I love having lots of data. It is also true that data makes some businesses, like web search, defensible. Web search is a long-tail business, meaning that there are a lot of very, very rare web queries, and so seeing what people click on when they search on all of these rare web queries does help the leading web search engines have a much better search experience. So big data is great when you can get it. But I think big data is also sometimes overhyped, and even with a small data set, you can still often make progress. Here's an example. Let's say you're building an automated visual inspection system for the coffee mug. So you want to automatically detect that the coffee mug on the right is defective. Well, if you had 1 million pictures of good coffee mugs and defective coffee mugs, it'd be great to have that many examples of pictures of good and bad coffee mugs to feed to your AI system. But I hope that you have not manufactured 1 million defective coffee mugs, because that feels like a very expensive thing to have to throw away. So sometimes with as few as 100 pictures, or maybe 1,000, or sometimes maybe as few as 10, you may be able to get started on a machine learning project. The amount of data you need is very problem dependent, and speaking with an AI engineer or an AI expert would help you get a better sense. There are some problems where 1,000 images may not be enough, where you do need big data to get good performance, but my advice is don't give up just because you don't have a lot of data to start off with, and you can often still make progress even with a small data set. In this video, you saw a brainstorming framework and a set of criteria for trying to come up with projects that hopefully can be doable with AI and that are also valuable for your business. Now, having brainstormed a list of projects, how do you select one or select a small handful to actually commit to and work on? Let's talk about that in the next video. Maybe you have a lot of ideas for possible AI projects to work on, but before committing to one, how can you make sure that this really is a worthwhile project? If it's a quick project that might take you just a few days, maybe just jump in right away and see if it works or not, but some AI projects may take many months to execute. In this video, I want to step you through the process that I use to double check if a project is worth that many months of effort. Let's take a look. Before committing to a big AI project, I will usually conduct due diligence on it. Due diligence has a specific meaning in the legal world, but informally, it just means that you want to spend some time to make sure what you hope is true really is true. You've already seen how the best AI projects are ones that are feasible, so is something that AI can do, as well as valuable. We really want to choose projects that are at the intersection of these two sets. So to make sure a project is feasible, I will usually go through technical diligence. And to make sure that the project is valuable, I will usually go through a business diligence process. Let me tell you more about these two steps. Technical diligence is the process of making sure that the AI system you hope to build really is doable, really is feasible. So you might talk to AI experts about whether or not the AI system can actually meet the desired level of performance. For example, if you are hoping to build a speech system that is 95% accurate, consulting with AI experts or perhaps reading some of the trade literature can give you a sense of whether this is doable or not. Or if you want a system to inspect coffee mugs in a factory and you need your system to be 99% accurate, again, is this actually doable with today's technology? A second important question for technical diligence is how much data is needed to get to this desired level of performance? And do you have a way to get that much data? Third would be engineering timeline to try to figure out how long it will take and how many people it will take to build the system that you would like to have built. In addition to technical diligence, I will often also conduct business diligence to make sure that the project you envision really is valuable for the business. So a lot of AI projects will drive value through lowering costs, for example, by automating a few tasks or by squeezing more efficiency out of a system. A lot of AI systems can also increase revenue, for example, driving more people to checkout in your shopping cart. Or you may be building an AI system to help you launch a new product or a new line of business. So business diligence is the process of thinking through carefully for the AI system that you're building, such as a speech recognition system that's 95% accurate or a visual inspection system that's 99.9% accurate, would allow you to achieve your business goals. Whether your business goal is to improve your current business or to even create brand new businesses in your company. When conducting business diligence, I'll often end up building spreadsheet financial models to estimate the value quantitatively, such as estimate how many dollars are actually saved or what do we think is a reasonable assumption in terms of increased revenue, and to model out the economics associated with a project before committing to many months of effort on a project. Although not explicitly listed on this slide, one thing I hope you also consider doing is a third type of diligence, which is ethical diligence. I think there are a lot of things that AI can do that will even make a lot of money, but that may not make society better off. So in addition to technical diligence and business diligence, I hope you also conduct ethical diligence and make sure that whatever you're doing is actually making humanity and making society better off. We'll also talk more about this in the last week of this course as well. As you're planning out your AI project, you also have to decide, do you want to build or buy? This is an age-old question in the IT world, and we're facing this question in AI as well. For example, hardly any companies build their own computers these days. They buy someone else's computers, and hardly any companies build their own Wi-Fi routers, just buy a commercial Wi-Fi router. How about machine learning and data science? Machine learning projects can be in-house or outsourced. I've seen both of these models used successfully. Sometimes if you outsource a machine learning project, you can have access much more quickly to talent and get going faster on a project. It is nice if eventually you build your own in-house AI team and can also do these projects in-house. You hear more about this when we talk about the AI transformation playbook in greater detail next week. Unlike machine learning projects though, data science projects are more commonly done in-house. They're not impossible to outsource. You can sometimes outsource them. But what I've seen is that data science projects are often so closely tied to your business that it takes very deep day-to-day knowledge about your business to do the best data science projects. And so just as a percentage, as a fraction, I see data science projects in-house more than machine learning projects. Finally, in every industry, some things will be industry standard, and you should avoid building those. A common answer to the build versus buy question was build the things that are going to be quite specialized to you or completely specialized to you, or that allow you to build a unique defensible advantage. But the things that will be industry standard, probably some other company will build, and it'll be more efficient for you to just buy it rather than build it in-house. One of my teams had a really poetic phrase, which is don't sprint in front of a train. And what that means is if this is a train running on the railway tracks, and there's the little chimney with the puff of smoke, what you don't want to do is to be the person or the engineer trying to sprint faster and faster ahead of the train. The train is the industry standard solution. And so if there's a company, maybe a startup, maybe a big company, or maybe an open source effort that is building an industry standard solution, then you may want to avoid trying to run faster and faster to keep ahead of the train, because even though you could sprint faster in the short term, eventually the train will catch up and, crush someone trying to sprint in front of a train. So when there's a massive force of an industry standard solution that is being built, you might be better off just embracing an industry standard or embracing someone else's platform rather than trying to do everything in-house. We all live in a world of limited resources, limited time, limited data, limited engineering resources. And so I hope you can focus those resources on the projects that are most unique and will make the biggest difference to your company. Through the process of technical diligence as well as business diligence, I hope you can start to identify projects that are potentially valuable or that seem promising for your business. If the project is a big commitment, maybe it'll take many months to do, it's not unusual for me to spend even a few weeks conducting this type of diligence before committing to a project. Now, say you found a few promising projects. How do you engage with an AI team? How do you work with an AI team to try to get these projects done? Let's talk about that in the next video. Say you found an exciting project that you want to try to execute on. How do you work with an AI team on this project? In this video, you learn how AI teams think about data and therefore how you can interact with AI teams to help them succeed on a project. Now, there is one caveat, which is what if you have a cool idea, but you don't have access to an AI team? You don't have access to any AI engineers. Fortunately, in today's world, if either you yourself or you can encourage some of your engineering friends to take an online course or two on machine learning or deep learning, that often will give them enough knowledge to get going and make a start of an attempt, make a reasonable attempt on these types of projects. So let's talk about how you can work with an AI team. First, it really helps your AI team if you can specify an acceptance criteria for the project. I've done a lot of work in automated visual inspection, so I'm going to use that as a running example in these few slides. Let's say your goal is to detect defects in coffee mugs with at least 95% accuracy. So that can be your acceptance criteria for this project. But 95% accuracy, how do you measure accuracy? One of the things that the AI team would need is a data set on which to measure their accuracy. So a data set is just a set of pictures like these, together with the labels with the desired output B, that the first two coffee mugs are okay and the third one is defective. So as part of your specification for the acceptance criteria, you should make sure that the AI team has a data set on which to measure the performance so that they can know if they've achieved 95% accuracy. The formal term for this data set is called a test set, and the test set may not need to be too big. Maybe 1,000 pictures will be just fine for this example. But if you consult with an AI expert, they can give you a better sense of how big the test set needs to be for them to be able to evaluate whether or not they're getting to 95% accuracy. One novel part of AI systems is that the performance is usually specified in a statistical way. So rather than asking for an AI system that just does something perfectly, you see very often that we want an AI system that performs at a certain percentage accuracy, like this example here. So when specifying your acceptance criteria, think of whether your acceptance criteria needs to be specified in a statistical way, where you specify on average how well it does or what percent of time it has to get the right answer. Let's dive more deeply into the concept of a test set. This is how AI teams think about data. AI teams group data into two main data sets, the first called the training set, and the second called the test set, which we've already talked a bit about. The training set is just a set of pictures together with labels showing whether each of these pictures is of a coffee mug that is okay or defective. So the training set gives examples of both the input A, the pictures of the coffee mugs, as well as the desired output B, whether it's okay or defective. And so given this training set, what a machine learning algorithm will do is learn, in other words, compute or figure out some mapping from A to B so that you now have a piece of software that can take as input the input A and try to figure out what is the appropriate output B. So the training set is the input to the machine learning software that lets it figure out what is this A to B mapping. The second data set that an AI team will use is the test set. And as you've seen, this is just another set of images that's different from the training set, also with the labels provided. The way an AI team will evaluate their learning algorithm's performance is to give the images in the test set to the AI software and see what the AI software outputs. For example, if on these three test set images, the AI software outputs okay for this, and also okay for this, then we would say that it got 2 out of 3 examples right. And so that's a 66.7% accuracy. In this figure, the training set and test set are both only 3 pictures. In practice, both of these data sets would be much bigger, of course. And you find that for most problems, the training set is much bigger than the test set. But you can talk to AI engineers to find out how much data they need for a given problem. Finally, for technical reasons, some AI teams will need not just 1, but 2 different test sets. If you hear AI teams talk about development or dev or validation sets, that's the second test set that they're using. The reasons why they need 2 test sets is quite technical and beyond the scope of this course, but if an AI team asks you for 2 different test sets, it's quite reasonable to try to provide that to them. Before wrapping up this video, one pitfall I want to urge you to avoid is expecting 100% accuracy from your AI software. Here's what I mean. Let's say this is your test set, which you've already seen on the last slide. But let me add a few more examples to this test set. Here are some of the reasons it may not be possible for a piece of AI software to be 100% accurate. First, machine learning technology today, despite being very powerful, still has limitations and they just can't do everything. And so you may be working on a problem that is just very difficult, even for today's machine learning technology. Second, insufficient data. If you don't have enough data, specifically if you don't have enough training data for the AI software to learn from, it may be very difficult to get a very high level of accuracy. Third, data is messy and sometimes data can be mislabeled. For example, this green coffee mug here looks perfectly okay to me, so the label of it being a defect looks like an incorrect label, and that would hurt the performance of your AI software. And data can also be ambiguous. For example, it looks like this coffee mug has a small scratch over there, and it's a pretty small scratch. So maybe we will think it is still okay, but maybe this should actually have been a defect. Or maybe even different experts won't agree if this particular coffee mug is okay and should pass the inspection step. Some of these problems can be ameliorated. For example, if you don't have enough data, maybe you can try to collect more data, and more data will often help. Or you can also try to clean up mislabeled data, or try to get your factory's experts to come to better agreement about these ambiguous labels. So there are ways to try to make these things better, but a lot of AI systems are incredibly valuable even without achieving 100% accuracy. So I would urge you to discuss with your AI engineers what is a reasonable level of accuracy to try to accomplish, and then try to find something that passes both technical diligence as well as business diligence without necessarily needing 100% accuracy. Congratulations on finishing all the videos for this week. You now know what it feels like and what it takes to build an AI project, and I hope you start brainstorming and exploring some ideas. There is one more optional video describing some of the technical tools that AI teams use that you can watch if you wish. But either way, I look forward to seeing you next week, where you learn how AI projects fit in the context of a bigger company. Look forward to seeing you next week. When you work with AI teams, you may hear them refer to the tools that they're using to build these AI systems. In this video, I want to share with you some details and names of the most commonly used AI tools so that you'll be able to better understand what these AI engineers are doing. We're fortunate that the AI world today is very open, and many teams will openly share ideas with each other. There are great machine learning open source frameworks that many teams will use to build their systems. So if you hear of any of these, TensorFlow, PyTorch, Keras, MXNet, CNTK, Caffe, PaddlePaddle, Scikit-learn, R, or Weka, all of these are open source machine learning frameworks that help AI teams be much more efficient in terms of writing software. A lot of AI technology breakthroughs are also published freely on the internet on this website called Archive, spelled like this. I hope that other academic communities also freely share their research, since I've seen firsthand how much this accelerates progress in the whole field of AI. Finally, many teams will also share their code freely on the internet, most commonly on a website called GitHub. This has become the de facto repository for open source software in AI and in other sectors than AI. And by using appropriately licensed open source software, many teams can get going much faster than if they had to build everything from scratch. So for example, if I search online for face recognition software on GitHub, you might find a web page like this. And if you scroll down, this actually has a pretty good, very readable description of software that is made available on this website for recognizing people's faces and even finding parts of people's faces. There's just a ton of software that is freely downloadable for doing all sorts of things on the internet. And just double check the license, or AI team would double check the license before using it in a product, of course. But a lot of the software is open source or is otherwise very permissively licensed for anyone to use. Although GitHub is a technical website built for engineers, if you want, you should feel free to play around GitHub and see what other types of AI software people have released online as well. In addition to these open source technical tools, you often also hear AI engineers talk about CPUs and GPUs. Here's what these terms mean. A CPU is the computer processor in your computer, whether it is your desktop, your laptop, or a compute server off in the cloud. CPU stands for Central Processing Unit, and CPUs are made by Intel and AMD and a few other companies. This does a lot of the computation in your computer. GPU stands for Graphics Processing Unit. Historically, the GPU was made to process pictures. So if you play a video game, it's probably a GPU that is drawing the fancy graphics. But what we found several years ago was that the hardware that was originally built for processing graphics turns out to be very, very powerful for building very large neural networks, or very large deep learning algorithms. Given the need to build very large deep learning or very large neural network systems, the AI community has had this insatiable hunger for more and more computational power to train bigger and bigger neural networks. And GPUs have proved to be a fantastic fit to this type of computation that we need to have done to train very large neural networks. So that's why GPUs are playing a big role in the rise of deep learning. NVIDIA is a company that's been selling many GPUs, but other companies, including Qualcomm, as well as Google, making its own TPUs, are increasingly making specialized hardware for powering these very large neural networks. Finally, you might hear about cloud versus on-premises, or for short, on-prem deployments. Cloud deployments refer to if you rent compute servers, such as from Amazon's AWS or Microsoft's Azure or Google's GCP, in order to use someone else's servers to do your computation, whereas an on-prem deployment means buying your own compute servers and running the servers locally in your own company. A detailed exploration of the pros and cons of these two options is beyond the scope of this video. A lot of the world is moving to cloud deployments, but if you search online, you find many articles talking about the pros and cons of cloud versus on-prem deployments. There is one last term you might hear about, which is edge deployments. If you are building a self-driving car, there's not enough time to send data from a self-driving car to a cloud server to decide if you should stop the car or not, and then send that message back to the self-driving car. So the computation has to happen usually in a computer right there inside the car. That's called an edge deployment, where you put a processor right where the data is collected so that you can process the data and make a decision very quickly without needing to transmit the data over the internet to be processed somewhere else. If you look at some of the smart speakers in your home as well, this too is an edge deployment where some, not all, but some of the speech recognition task is done by a processor that is built in right there into the smart speaker that is inside your home. The main advantage of edge deployments is it can increase response time of the system and also reduce the amount of data you need to send over the network. But there are many pros and cons as well about edge versus cloud versus on-prem deployments that you can also search online to read more about. Thanks for finishing this optional video on the technical tools that AI engineers use. Hopefully, when you hear them refer to some of these tools, you start to have a better sense of what they mean. I look forward to seeing you next week.